Good morning and welcome everyone to the AMS Maryam Mirzakhani lecture. My name is Ruth Charney. I'm serving as president of the American Mathematical Society, and it's my honor to introduce this talk. The AMS Council established this lecture series in 2018 to honor Maryam Mirzakhani, the first woman to win a Fields Medal. It is a great pleasure to welcome this year's Mirzakhani speaker, Professor Ling from Louisiana State University. Professor Long received her PhD in 2002 from Pennsylvania State University. She spent 1 year as a postdoc at the Institute for Advanced Study before moving to Iowa State as an assistant professor. Then in 2013, she moved to Louisiana State University, where she is now a full professor. Professor Long's research lies in the area of number theory. She has made important contributions to the theory of hypergeometric arithmetic, modular forms, and elliptic surfaces. She has also been involved in various mentoring activities such as the Women in Numbers workshops and the resulting research networks. Her research work has been recognized by numerous honors, grants, and fellowships. Most notably, she was awarded the AWM Ruth Mischler Prize in 2012, and this year she was selected for the 2023 class of AMS Fellows. Congratulations, Ling Long. Today, Professor Long is going to lead us on a stroll in the garden of hypergeometric functions. Please welcome Professor Ling Long.
Thank you. Thank you, Ruth. I would like to thank everyone here to visit the garden of hypergeometric functions. And is the speaker okay to everyone? I just want to make sure. All right. I would probably need some time to warm up to be myself. All right. Just be patient. So the garden was built by generations of master gardeners, including Raymond and Gauss. I'm not going to be able to mention all names, and mainly I will show you 4 sections of the garden. So we will start from the oak garden, from where we will walk to the fields garden and perform a garden activity, how to measure a pie periodically. Then we will head south to the walk garden, and then there is another activity for you. We will be dissecting an hypergeometric onion. And then we will head west to the Hecker garden before we return to the oak garden from the grand finale. So let's start the walk. So this is an overview of the oak garden, and which I took from the oak alley plantation. And now let's start with the family DNA of a hypergeometric datum. So by which I denoted by HD. It consists of 2 multisets, one called alpha, one called beta. Elements in alpha are called AIs. They are chosen from non-zero rational numbers, and the length of alpha is called the length of the hypergeometric datum. Beta is another multiset of the same length. And the elements also in rational numbers, and the convention is B1 is 1. Given such a pair, the length is the length of the multiset. There is another notion called the level, which is the least common denominators of all the AIs and BJs. Such a pair is called primitive if AI minus BJ is not it's not an integer or 0 modulo z. And this pair is said to be self-dual, which is one notion I will need. If both alpha, beta, they are invariant under multiplication by -1 when modulo z. And in a more stronger sense, if multiplied by any c coprime to the level, the 2 multisets are both invariant modulo z. The pair is said to be defined over Q. For example, there are 2 examples which will pop up a few times. The first one with level 24 consists of 1/24 and 7/24. Clearly, it's not defined over Q. If I have 1/24, self-dual, at least I should see 23/24. The beta set consists of 1 and 5, 6. And the second one, the length 3, second example, if you look at that one, it is however defined over Q because alpha consists of 1/2, 1/3, and the other conjugate 1/3, which is 2/3. For the same reason, beta is also defined over Q, consists of 1, 1, 6, and the only other conjugate, 5, 6. The length is 3, the level is 6 for the second example. With a case like the second example, we will move on to compute what I call family DNA of the acorn. So it's computed in the following way. If you have a primitive hypergeometric datum defined over Q, now both AI and BJ are within the range from 0 to 1, including 1 but not 0. For any x within 0 to 1, we will consider a function. This function is a step function, counts how many elements in alpha they are less than or equal to x, subtracting how many of those in beta. So we get to a step function. So this is the second example I mentioned earlier, so I show you the graph. And with this graph, which is step function, we look at the maximum. In this case, it's 2. Take away the minimum, which is -1. The gap is called the weight of the hypergeometric datum. And another thing is, if we travel along the plot from 0 to 1, including the vertical ones, and if you travel each time when you get to an integral altitude, as long as the next move is going up, you do a marking and mark it by a small red circle. You collect all the markings in a set called C, and then you can get to a polynomial. It's constructed in variable t as summation over all i's in C, and then we let t raised to I in C raised to the minimum of the hypergeometric plot. And for the current case, we get to the polynomial, which is 1 plus t squared. And reading of the coefficients, we get to the so-called Hodge sequence, or the H sequence, which is 1, 1, 1 for the present case. And if we go back to the general case, we'll get to the hypergeometric differential equation for given alpha and beta. And it's written in terms of theta, which is t times d dt. This is an ordinary differential equation with only 3 variables, 0, 1, and infinity. The order of the differential equation will be m. So I will ask you, have you ever spotted any oak singularities? Or they are also called oak gals. So let me show you a picture. They are really, really very regular and smooth. And anyway, let's move on to the mathematical sign. So given A and K, we can define the Pochhammer symbol, which is going to be A times A plus 1 all the way to A plus K minus 1. Another way to write it will be in terms of quotient of 2 gamma values, gamma of A plus K over gamma of A. Actually, gamma function playing a more primary role in the study of classical hypergeometric functions than the Pochhammer symbol. And if you think about a hypergeometric datum as an acorn, which is a family DNA, now if you put it down into a position t, you can grow into a function or an oak tree. So it's written in terms of this formal power series, in terms of Pochhammer symbols. And I'm not going to read everything on the screen. And another notion I will need will be the truncation. If I have a non-negative integer m, if I put in a subscript next to the hypergeometric function, that means I will truncate everything after m. So I get to a polynomial. So with a tree, we further propagate into a forest or local system. And this gives us a local system, and the local solutions are forming a solution. The vector space, the dimension of the vector space is the length of the hypergeometric datum. So we get to a so-called monogeometry representation of the fundamental group, which is the base Riemann surface CP1, take away the 3 singularities. So it's the fundamental group sending to the image, which is in GLNC. It's fixed up to conjugations. And if we look at the images of the simple loops around the three singularities, 0, 1, and infinity, the images will give us so-called local monogamy matrices. In particular, the local monogamy at 1, it's a very special one. It's called a pseudo-refraction, which means the local monogamy matrix at 1, taking away identity matrix of the same rank, has codimension 1. So this will be actually playing an important role for later examples popping up. And I will also mention that the images of the hypergeometric monogamic representation groups has been classified in a very fundamental group by Boykers and Hedman. Okay. So with that, we will conclude the walk in the Oak Garden and move on to the Fields Garden, featuring two important formulas. They are very useful for me as tools to build garden projects. The first one is called Clausen formula. The second one is called Whipple 7F61 formula. And there are two greenhouses on the screen. The smaller one on the left is a miniature greenhouse built by my younger daughter. And with the idea in mind, we built the actual greenhouse 1 year later. So if you find the right tool, you can finish any project that you would like to do. So also, I learned a fun fact when preparing my talk. Whipple is life-saving, and it's also for real. Okay. So let's start with the garden activity, how to measure a pie periodically. The story originated in the formulas of Ramanujan. Ramanujan wrote down 17 formulas for 1 over pi. One of them is shown on the screen. Basically, if you use the formal power series on the left-hand side of the equation, you will get to 4 over pi. And later, there are two pairs of brothers, Bowen brothers and Chodanovsky brothers, actually able to realize why such formula holds using the first formula I mentioned, Clausen formula. And such formulas are useful for actually computing the digits of pi very efficiently. Later, when Ham noticed, very interestingly, if you fix any prime number p you have in mind, maybe 3, might be 101, whichever you like. If you look at the same series on the top, you do the truncation from 0 to p minus 1. Surprisingly, you get to the p-adic approximation of pi, or 1 over pi, which is p, with a Legendre symbol in the front, up to a position of p to the 4th. And I was able to prove this conjecture using the second tool, which is the 7F61 formula. So now let's talk about finite fields. For my talk, each finite field, FQ, will have size Q, characteristic P, which is assumed to be odd. With such a finite field, if you look at homomorphisms from the invertible elements to C, it's forming a cyclic group. I use omega as a generator. And for base field, for the prime field, Q equals to P, I use the Legendre symbol to denote the unique quadratic character. So there are different versions of hypergeometric character functions by the work of John Green and Professor Nick Katz, and also Dermot McCarthy. And there's another kind of modification in the work of Boykers Cohen Mennett. Sometimes I refer it as BCM. And also in a very recent memoir that's written by my co-authors in the audience, Jenny Fuseli, Ravi Ramakrishna, not here, Holly Swisher, and Fountain Tu. So we give kind of a very parallel modification of the Green's version so that we can use the Galois perspective for a lot of discussions. And for the purpose of my talk, I'm going to just introduce, this is one of the formulations which is useful. If the size of the finite field is 1 modulo the level of the hypergeometric datum. For lambda inside the finite field, which is invertible, you can define the hypergeometric character sum, which is parallel to the classical setting, where everywhere you see gamma function, you replace by Gauss sum. And in particular, if the hypergeometric datum is primitive and defined over Q, the answer is going to be independent of which omega, which generator you're going to pick, because the value is a rational number. In that situation, we drop the reference to omega. And another cool thing about when the datum is defined over Q is that there is no more condition on Q being 1 modulo the level. So that condition can be greatly relaxed. And so let's move on to mention a very fundamental result. I will only mention the easiest case for me to state, which is due to cats, and the lifting part is due to BCM. So it says if you have a primitive hypergeometric datum defined over Q, then for any lambda, which is co-prime to the level and it's not 0, and if you also count how many elements in beta are in Z, well, all of a sudden, for any lambda you pick, you have a Galois representation of the absolute Galois group GQ. And you also know the dimension. When lambda is not 1, the dimension will be the same as the length of the representation. If lambda is 1, however, there is a one-dimensional drop. So it's n minus 1 instead. Another amazing thing is the representation is motivic, so you can compute what happens at Frobenius. P, if P is a good prime. It turns out the trace of the representation can be computed exactly by the hypergeometric character sum times possibly a power P. And the argument is 1 over lambda due to some convention over here. And in more general setting, if you remove define over Q and replace it by self-due, there is a similar result, which is also due to cats. And now let's see the Clausen formula, the first useful tool that I mentioned. So if you look at this formula, it tells you if you take a product of two 2F1 hypergeometric function, you get to a 3F2, which is like a miracle. So if you go slightly into the background, so what it tells you, the picture indicates is you do tensoring of a tree, 2-dimensional. You end up with a 4-dimensional branches, or 4-dimensional representation, but you are only seeing 3-dimensional structure on surface. In the background, there is a 1-dimensional piece which is hiding. So that's what the Clausen formula tells you. It's implicitly, it's 2 times 2 equals to 3. Actually, there's one thing in the shadow in the background. In particular, if you go back to the first example, we look at 127, 7 over 24, 7 over 24, and 1 and 5, 6 for the lower parameter. Then multiplying by, in some sense, it's complex conjugate in the sense that I did change 1 to 24 to 23 over 24. Altogether, the sum is 1, etc. You get to the 3F2 with additional radical in front of it. And the cool thing about the 3F2 is now the hypergeometric datum on the right-hand side is the same as the second example is defined over Q. That will actually give us a lifting of the Galois representation. And I would like to also mention that Ron Evans and John Green attained the finite field analog of the Clausen formula. Okay? So here is the second useful formula that I mentioned, which is called the Whipple 7F61 formula. It is an evaluation formula, which means on the left-hand side, if you read, there is a datum, there is an acorn, the length is 7, and the location I planted is 1. For the right-hand side, the datum is length 4, the location is also 1. Clearly, if you look at this formula, it tells you there is a certain degeneracy for the structure on the left. And if you look at the data on the left, the red color tells you it's not primitive. So it's imprimitive because the second column, the difference is 1, which is an integer. And also, it's a well-poised series in the sense that the sum of each column, if you add them up, you will get 1 plus 8, the same for each column. And so this picture down here tells you basically what's happening. It's the scenario I want you to think about. All the information encoded on the left-hand side is more or less like the purple flower. The right-hand side, however, only retains part of the information, which is the yellow statement in the middle. So something's missing. And one important question for us is what has been missing? So let's look at the self-dual version. So this is a project I joined with Winnie Lee and Fountain 2. We look at the self-dual version of the WIPO 7F61 formula. If I make it into self-dual means if I see C, I also have 1 minus C, etc. And if I imposing self-dual condition to both alpha and beta, we get to this formulation. There is additional P just for the convenience. Now, both series on the left and right-hand side will be terminating. And if you look at the Galois version of WIPO 7F61 formula, basically the setup is if we forget about the middle column, the left-hand side reduced to a hypergeometric datum, which is length 6. So we write down is alpha parameter is 1/2 C, 1 minus C, 1/2 F, 1 minus F, etc. And on the right-hand side, the hypergeometric data is 1/2, 1/2 F, 1 minus F. And if we both look at the arguments at 1, Katz's theorem tells you in the self-dual version, now the left-hand side corresponds to, there is a 1-dimensional drop. Hence, it's a 5-dimensional representation on the left-hand side. And the right-hand side now is only 3-dimensional. There is additional cyclotomic character. I have to do the tensoring to get to the P on the left-hand side of the first equation. And the leftover, it's a very precise 2-dimensional representation. I will show you in a later case what it looks like. Okay, so we will be finding the missing piece in the later presentation. So we move on to the p-adic, the Works p-adic garden. So this cauliflower is called romanestic cauliflower. So we grew it in our greenhouse. So it's a very kind of particular shape, very self-similar. So I will go back to see that in this garden to make highlights self-similarity and another thing I call hypergeometric superpower. Okay? So let's start with the self-similarity. So in this example, I give you hypergeometric datum, which is 1/2, 1/2 divided over Q. Beta is 1, 1. For this case, you can write down the coefficients of the power series in terms of binomial coefficient. In particular, for the current case, it's 2k choose k squared with a power of 2. If you look at any p-adic evaluations of the sequence, I pick 3 over here. You will get to a plot, which is on the right side of the slides. Based on this type of self-similarity, the work attained the following very fundamental result. I'm only stating the easiest version in this talk. If I have a hypergeometric datum which is defined over Q and primitive, in the works version, beta consists of all ones. Then the work tells you if you pick lambda, pick a P that you like, and then you pick, and also co-prime to the level, and then you pick any lambda, which is p-adically integral. Now you look at the ordinary assumption, which means you look at the truncation of your series at p minus 1. If it's not 0 modulo p, then you continue to look at quotients of 2 truncated hypergeometric series. The one on the top with argument lambda truncated at p to the s minus 1 over the other one, argument at lambda to the p, truncated at p to the 1 power less, also -1. Then this quotient is going to be convergent to a p-adic unit I call mu hd p lambda, modulo p to the s. In particular, when s equals to 1, the first truncation will be agreeing with the p-adic unit root modulo p power. And later in the talk, if I see anything which is stronger than this p to the 1 power, generically for all p, I will call it a supercongruence. Right. In particular, this is a paper recently appeared drawn again by my colleague Fanting Chu, Noriko Yuri, and Wading Zudli. So we gave a uniform, actually 2 uniform proof of a conjecture made by Philando Rodriguez Villegas. So his conjecture is originating in the study of rigid Calabi-Yau threefolds. So the statement is as follows. If you consider a pair of 2 integers starting from 2 and look at the multi-set of length 4 generated by 1 over d1 and 1 minus 1 over d1 to make sure it's self-due, and then 1 over d2 and 1 minus 1 over d2. If your multi-set is defined over Q, there are 14 such choices. And also in this case, if you look at beta to be all ones, then the conjecture was there is an explicit wave 4 Hecker-Caspito eigenform, which is normalized, such that if you do the truncation for any p bigger than 5, we can do the truncation. The truncated hypergeometric series at p minus 1 for any p bigger than 5 will be the same as the Peace coefficient of the wave 4 modular form depending on alpha, modulo the superpower, cubic superpowers p to the 3. So there are previous work by Cuban, McCarthy, Fuseli, and McCarthy. And to move on, I just want to mention later modular forms are labeled using the L function and modular form database. For example, f of 8 for AA stands for a modular form. The 8 stands for the level, 4 stands for the weight, and AA refers to the character. So let me show you this example. I put together an ID for an oak tree. The family name of the oak tree is called 1 half, 1 half, 1 half, 1, 1, 1. So if you compute the corresponding hypergeometric plot, you will get to the generic Hodge sequence, which is 1, 1, 1, 1. And the first name of the tree I chose is 1. So Zage computed the value of this tree. So Zage evaluated this 4F3 with all the 1 half on top and all ones down here at 1. Zage told us that the value will be the L value of a modular form, which is the A4AA we have seen at value 2. And modularity is due to Scott Algren and Ken Ono. They showed that if you evaluate a hypergeometric character sum at P, if P is odd, you will get to P's coefficient of the same modular form again plus P. And this actually tells us that individually, the Hodge sequence has a degeneration because it's at 1, because it's a pseudo-refraction, so it's only 3-dimensional. Decomposes into 2 pieces, correspond to the way 2 part. The Hodge sequence is 1, 0, 0, 1. And the next one is the supercongruence one attained by Cuban. So he said his result is one instance of the previous result I showed you. If you look at the truncated hypergeometric series, you get to the Peace coefficient of the same modular form again, modulo the cubic power. So I will call this case the super S power is 3 for this current oak tree. So last year, Michael Allen, which is also in the audience, proved a more actually intricate cases. So he attained similar QBS power superconferences for all other primitive lengths for wave 4 hypergeometric datum, relaxing the condition beta to be all ones. So it's actually more subtle cases he handled. I'm not going to go through all the details, but going to tell you. So this is actually a very nice heuristic made by David Roberts in the back and also Fernando Rodriguez Villegas. So they said that, hey, I have a way to predict the superpower dimension. The superpower is going to be 1, which is the generic superpower, plus, if you look at the corresponding individual Hodge sequence, if there is a 0 gap in the middle, so it will be 1 plus how many 0 between the ones. So that's basically the idea. And if you ask me how to look for such oak trees with the 0 gap or hole in the middle, I would say that how about the hypergeometric Whipple procedure? All right. To my surprise, when I checked Mayo Clinic, it says that the real Whipple procedure is a difficult and demanding operation, and it's of life-saving. And for me, it saved me from this very difficult and demanding job of finding a holy oak tree. So we are able to find it using the hypergeometric Whipple procedure. All right, so this is now the second activity, how to dissect a hypergeometric onion. So in this case, the last name of the onion is very long. So I'm not going to read everything for you. The first name, again, is very short. It's 1. And if you have this hypergeometric onion, if you're trying to see whether they fit into the philosophy of David Roberts and Fernando Rodriguez Villegas, we use the Whipple formula. Use the parameters CF to be the pair 1/2 and 1/3. We actually get 3 slices of the onion. The first slice, the outer layer, is a wave 6 modular form of level 4. The middle layer is a wave 4 modular form corresponding to the 4F3 on the right-hand side Whipple formula. There is also an inner layer, which is P. Clearly, this decomposition tells us that there is actually motifly, the representation has a decomposition into 3 pieces. 2 plus 2 plus 1 are the corresponding dimensions. The outer one, wave 6, the Hodge sequence is 1 with 4 zeros in the middle and 1. The middle one, wave 4, with a P in the front. So there is a shift. Start from 0, it's 1, 2, 0, and 1, etc. And if we look at the corresponding supercongress they're trying to predict, it actually matches very well for all P bigger than 3. If I look at the truncated hypergeometric series, this time with a P to the front to make sure it's p-adically integral, we will get to the P's coefficient of the wave 6 modular form, raised to P plus 1, 1 plus 4 holes in the middle is P to the 5. Likewise, if we look at the middle piece, it will be differential of second kind. So we go back to Whipple's original formula, 7F6, put back what I took away, which is 5, 4, and 1, 4. We look at the truncation this time. It matches with the waveform modular form, modulo 1 plus the 2 hole in the middle. So that's what we actually be able to find very, I mean, to us, it's very kind of interestingly, we can use the hypergeometric Whipple procedure to produce. This is a very nice case matching their heuristic. All right, so let's now move on to the Hecker garden. Originally, I imagined Hecker garden, because of there are lots of operators, it will be like a Japanese garden. There are maples, etc. It turns out another thing I learned, Hecker is hatch. So it means all the bushes are shaped very regularly. All right. And the center of the hexagon for me is the Sawt Theorem. So it says the following: if we go back to the hypergeometric datum, length 2, so alpha now consists of AB, beta consists of 1C. And if I have such a hypergeometric datum, we can look at the corresponding differential equation, which is order 2. And now pick any Z0, which is located on the complex upper half plane, and look at any two solutions, linearly independent near Z0. And the ratio of these two, F and G, is called a Sawt map. It will map the upper half plane, including the real line, into a triangle, which is colored in pink. And the three vertices will be the images of 0, 1, and infinity. And we also know the corresponding angle. At 0, the angle is P. This is a different P, which is 1 minus C absolute value times pi. The angle at 0 is that. At 1 will be Q times pi, which is absolute value C minus A minus B. And the angle at infinity will be R pi. So here I'm assuming PQR are less than 1. In particular, this example below, I'm picking A to be 1/2, B to be 1/2, and C to be 1. Fitting into the formula, you will see PQR are all zeros. And the pink triangle corresponds to a black triangle. Let's start with the middle one. So this is the image of the upper half plane. And you can also imagine the image of the lower half plane will be turning to, say, the white triangle in the middle next to it. Start from this black and white triangle, we can do refractions. Keep reflecting those triangles at the boundary. We get a tessellation of the upper half plane, which is conformal to the open disk. So this is the picture I'm telling you. And also, each point, say if you pick the middle black triangle, each interior point has a meaning in terms of parametrization. A parameterized elliptic curve with two torsion structure. So in more general setting, if PQR are both 1 over an integer, at least 2, including infinity, we can use even many refraction to form a so-called triangle group. So it will be denoted by gamma of E1, E2, and E3. So this is the generator relation that I wrote down on the screen. And so this triangle group corresponding to the space tiling. In particular, if we focus on the case P plus Q plus R less than 1, like the previous example, we have the sum is 0. So we get a tessellation of the upper half plane. In the second example, we are going back to the first hypergeometric datum, with 1/24, 7/24, and 1 and 5/6. If you computed PQR, P will be 1/6, Q will be 1/2, R will be 1/4. So we get to the triangle group, which is 2, 4, 6. This turns out to be an arithmetic triangle group classified by Takeuchi. So this means this group, I can have an embedding. There is a nice map given in the paper by Clark and Roy, how to send the generators to 3 matrices in SR to R. Using the embedding, so you can check whether the resulting kind of matrices, the group is commensurable with the non-one element of a maximum order of a quaternion algebra. In the present case, the quaternion algebra has discriminant 6. And so we can actually start from any black triangle and propagate. The white one will be the images of the lower half plane as before. Just like the previous case, each black point, interior point, also has a parametrization meaning. A parametrizing two-dimensional abelian variety with quaternion multiplication by the quaternion algebra, right? So let's quickly end this talk by telling you this is a result by Sawt algorithm. We know that once you get universal elliptic curve, you can use that to compute many different things, including Hecker operators. So this is a nice result by Sawt algorithm telling us that if we go back to the infinity-infinity group, which is isomorphic to gamma 2, you can compute the corresponding space of cusp form using the character sum, right? And very recently, my collaborators, Jerome Hoffman, Winnie Lee, Fanting Tu, and I able to attain a very parallel result. This is a harder case because we try very hard to find explicit models for the two-dimensional abelian variety. And it's not kind of working exactly as what we expected, but somehow we are able to bypass the finding. We go directly using the hypergeometric motif. So based on Clausen formula, the 246 data I gave you is not defined over Q, but I can make it defined over Q using Clausen formula. And then we use Katz's rigidity theorem for L-weighted sheaf, plus some information on the special fibers satisfying complex multiplication by two groups of papers, one by Barbara Granat, another one by Yifan Yang. So we are able to write down now also for 246. The forms are far more difficult to understand. There is no more Q expansion. Somehow we still be able to compute the piece Hecker operator using the character sums. All right. So with that, let's go back to the oak garden for the grand finale. Right. So this is the official picture I took from the oak alley plantation. It's marvelous. So start from very tiny acorn. If you plant them correctly, if you be waited very patiently, if you develop them fully, you get to a magnificent view. And thank you. Thank you for visiting. So this is a picture of LSU. All right. So I'd like to thank everyone for being here, sharing this walk with me for the garden that I enjoy. And I would like to thank all my collaborators. In particular, I would like to thank my long-term mentor, Winnie Lee, and Noriko Yuri, who's not able to come today. Thank you, Winnie. Thank you, everyone.
Let's thank Ling Long for a very interesting talk, and I have to say, you win the prize for the best pictures, no question about it. So
Thank you.
thank you for that.
Thank you.
If we have a little time for questions. If anybody has questions, can you come to one of the microphones in the aisle so we can hear your questions?
Or you can ask me later.
Or you can ask later. If anybody? No, I don't see anybody. Well, in that case, let's give her another round of applause for a very nice talk.
Thank you. Thank you.
Amazing.